Hello and welcome to AutoInform. My name is Frank Massey and today I have the pleasure of introducing BG Products, as this is a joint presentation introducing a new concept in the recovery and servicing of DPF systems. Let's begin by taking a look at the DPF, what it is, how does it function. This is just an example of a DPF. They come in all shapes and sizes. This is rather a large one, to be honest. It's not quite as close coupled as I would have liked. It's a separate catalyst and a separate DPF. The catalyst is an oxidation catalyst and the DPF is a storage device, an accumulator, where the carbon is either converted to carbon dioxide or stored for a process of recovery whilst the vehicle is being driven. The construction of the DPF is quite important. I want to just give a brief overview of how the catalyst is constructed. It's a silicon carbide substrate. It's a honeycomb formation. It's coated with aluminium oxide and s.r.o, which is porous. Now it's porous to the gaseous parts of the exhaust stream. So in other words, those gases which are of a small molecular size will pass through the porous part of the DPF into the atmosphere. The carbon molecules, most of which, and there's two types of carbon molecules unfortunately, some of the subparticles are of a size that will be captured and stored, if you like, in the DPF, and there are nanoparticles which will pass through. Now we're dealing with those particles which are contained and stored and produce a blockage. Those are the particles we're dealing with. Another very important part of the functionality of the DPF is that there is a platinum coating. So we've got a silicon carbide substrate, it's coated aluminium oxide and s.r.o. On top of that, there is a platinum coating. The platinum is vital for the conversion of soot into carbon dioxide. Now, I mention this as a critical part of the phase because under normal conditions, given favourable conditions whilst the vehicle is being driven, that conversion should be done passively. In other words, with no intervention by the driver or the control systems within the vehicle, including the PCM, that conversion of carbon into carbon dioxide should take place passively. That's passive generation or passive regeneration. If the conditions are adverse, in other words, that the exit temperature of the gases, and we'll come to that a little in more detail later on, are not suitable, and we're talking 250, 350 as a starting point for correct conversion of soot into carbon dioxide. If those gas temperatures are not reaching that value, then the soot will begin to be stored at the rear end of this DPF. The leading edge where the platinum, it's a zonal coat. In other words, there's more platinum at the front and very little at the rear. The idea is that the platinum will help convert the soot into carbon dioxide, with storage of the untreated subparticles should retain at the back end. So it's important that that platinum coating is there. Now, sadly, there are products on the market, replacement products, that do not have that platinum coating. And that is very critical because if you can't go through the passive phase of regeneration, the next stage, when pressure builds up, and there are a number of devices, DPF pressure sensors, this is one example. This is what they call a differential pressure sensor. It measures pressure before the DPF and pressure after the DPF, and it reports back a change in voltage, which represents the pressure within the DPF. If that pressure becomes excessive, and there are various phases of this pressure build-up, the ECU will take over a strategy, a recovery strategy called active regeneration, and it will command certain components to increase. It's called a targeted increase in exhaust gas. And the idea is that above and beyond normal temperatures, they will be raised to a point that will help burn off, oxidize the stored soot. Now, if that process becomes ineffective, the pressure will continue to increase, reported back through this. And also there's temperature sensors which also report an inefficiency of the flow across the DPF. If the data that's being received by the ECU suggests that that blockage has reached a point where no longer it has control, then it will go into some kind of default and you'll have mill lights, warning lights on the dash. Now, it may well be, if that's the case, that there is a repair requirement before you start to consider a service and a recovery process with the DPF. So it's important that you carry out a diagnostic process. And the first stage of that, of course, is to use a scan tool to have a look at the information stored in the ECU as regards functionality and accuracy of all these sensors. That's very, very important. In other words, you must fix the faults before you start the recovery phase. That's very important. As part of the overview of the DPF system, I think it's important perhaps just to focus on some of the more critical components, although it's important that all of the components function correctly. One of the most critical components that often does add to the problems of DPF blockage is the EGR valve. Now, the EGR valve suffers the same problems that the DPF substrate suffers, which is excessive carbon deposits preventing correct closure and operation. So it's absolutely crucial that works properly. That may need some proprietary work, replacement, cleaning or whatever to ensure that component's working properly. I mention that because there may not be a DTC that accurately represents the functionality of that component. We've had them where they've been partially open and there's been no DTC to suggest an error. So it's very important that it's known to be closing thoroughly, and there are tools and methods of achieving that. The air mass meter. The value from this is part of an algorithm that the ECU uses to predict and calculate functionality of the DPF and, of course, achieve the right stoichiometric ratio in the engine. So these can drift in value as well without reporting a DTC. So once again, it's important you understand the values of these and know that they're right. I've already mentioned the DPF sensor, the differential pressure sensor. That converts pressure into voltage. There are essentially two types. This is differential. There are some examples where it's a single aperture, where it's measuring total pressure in the exhaust stream. That's also mounted before the DPF. So theoretically, there could be a blockage further down, and that also would be reported by that device. This component, of course, measures differential. So be careful that there isn't a blockage further down the system also. So once again, understanding the efficiency of the exhaust stream is quite important. And another crucial component during the regeneration process is a wideband lambda sensor. This monitors very carefully the stoichiometric ratio of the engine during the DPF regeneration phase, and this combined with temperature sensors, and I say there are normally 3 in a system, it refers from the value of these components to an algorithm to predict the loading or the blockage of the DPF, and also to calculate additional fuel during the active regeneration phase. The additional fuel is post-compression, is introduced into the DPF once again to raise the combustion temperatures or the temperature in the DPF in order to convert soot into carbon dioxide. So this process of converting soot into CO2 is really what we're going to focus on. So much for the functionality. There's a lot more involved. It's not intended to be an instructional video on how DPFs work or even a diagnostic process, but to understand that the functionality of all these components fitted on the engine, they must all function. There cannot be a repair scenario prior to this service that we're going to introduce. Before we move on to the delivery mechanism, I'd like to introduce the actual product responsible for converting soot into carbon dioxide. It's delivered into the engine whilst it's running. The point I'd like to emphasize here is that this service is actually a complete service introduced into the air intake system at the throttle body, and therefore will treat all of the components from that point on right the way through to the DPF. So although we're concentrating perhaps on the recovery and service of the DPF, please don't forget the fact that intake swirl flaps, EGR valves, engine intake manifold, the back of the valves, eventually through the turbo, and finally, of course, creating a situation within DPF that will help convert that stored soot back into CO2. What I'd like to do at this stage in the presentation is to present the VIA, the 12Q VIA. This is an entirely revolutionary concept in the service and recovery of DPF systems. So I'd like to talk about how it achieves that, what the essential adjustable parameters are, and why it's so effective in achieving the results which it does, which is the removal or conversion of soot. Now, I think the platform is designed to control the delivery of the aqueous solution into the engine. Now, there's a number of very important critical components. Let me talk about the basic control functions on the tool first. We'll talk about what the parameters are. There is a pressure gauge, that's the delivery pressure of the solution. That's normally set around 6 bar, but it is adjustable. There is a heater switch, so the product is heated. And there is a vacuum gauge. Now, I tend not to try, I see vacuum as still as a pressure, but a pressure that's below that of atmosphere. But it's important that the vacuum, or the vacuum that's created, and it's created by this device, I'll come back to this in a moment, matches engine speed. So it's important that this dial is a key part of the control functionality and the delivery of the product. There is the fill port, so the product is filled here. The control valve for introducing the product into the engine whilst the engine's running is this device. It's a simple on-off device. The delivery hose, as you can see, and it also carries the vacuum connector as well. So if we just take a quick look at the intake manifold, you can see this product's being delivered directly into the throttle body intake system. It's essential, by the way, that the E-jar valve is maintained in a closed position. Now, I use that phrase quite loosely because there's different ways of achieving that, and that will depend on the engine application, but it's important the E-jar is closed. This is the measurement of vacuum. Having created a venturi, a restrictor, you'll create a negative pressure. And that negative pressure is monitored by that vacuum gauge. It's important that we match that to engine speed. So 15 inches of mercury would equate to 1,500 RPM. That's quite important. The jet housing, the nozzle, there's a delivery jet, that's that part of the assembly, and of course a variety of connection hoses. So the connection is quite flexible, doesn't take long to set up. Most vehicles, this can be set up in a matter of 10-15 minutes. And this is one of the more awkward applications, and this is taking around that sort of time. So much for the overview of the actual delivery mechanism. These devices, we call them a venturi, a shredder, a vortex generator. They do several things. They allow an introduction of measurement of vacuum. They allow the housing of the delivery jet. So one of the variables for delivering the product into the engine is the size of the jet. The other variable is the amount of air that's being allowed to be introduced past this restriction, and this is controlled by a number of drillings around the circumference of that device, and they are simply numbered 4, 5, 6, 7, 8, and so on. So that refers to the number of apertures. That controls the amount of air and therefore has a direct relationship to the stoichiometric ratio of the engine whilst it's running. That also is a very important consideration, and we'll come back to that a little later on in the actual filming of the process whilst it takes place. The other variable, of course, is the delivery pressure. I referred to the gauge. That's adjustable. It's normally set around 6 bar, but it is adjustable. And of course, the final adjustment parameter, also very important, and it's going to be a key part of the process, is the speed at which you run the engine. Because what we're going to do initially is run the engine at low speed, setting this all-important vacuum to match engine speed. So we're aiming for around 15 inches of mercury and around 1500 RPM. And we're going to load the DPF. Now, what I mean by load the DPF is saturate it with the product, because that's going to create the environment from which then we are going to raise the temperatures in the DPF, which will then convert the soot into CO2. So essentially, in simplistic terms, that's what we're going to achieve. At this stage of the presentation, I'd like just to take perhaps a step back and offer a number of opportunities from which you can gather information to establish how badly blocked the DPF is. I'll try and get them in some kind of chronological order, taking into account accessibility to tools and equipment. The most simplistic opportunity is to measure pressure. You can use a gauge for that, so by removing the hose from the DPF sensor and inserting a gauge, the gauge need only go to 1 bar, so from 0 to 1 bar will be sufficient, and simply measure pressure. You could use a multimeter, measuring the voltage output from the differential pressure sensor. You could use an oscilloscope, and in a moment I'd like to introduce that very method because this diagnosis we've carried out in this vehicle was done with the oscilloscope, and I'd like to just talk about the advantage of looking at the profile. And of course, another very obvious choice is the scan tool. Now, generically, I think it's technically the correct process to use a scan tool first. It's non-intrusive. In other words, you don't have to dismantle or change the conditions of the vehicle. It's non-intrusive, and it gives you a lot of very vital data on a lot of different parameters. We mentioned about DTCs and faults, and measurement parameters is very, very important. Let me just take a look at what information we've gained. We've already conducted a fairly thorough examination of this vehicle. We began with serial data. The tool is still attached to the car. We'll be relying on that during the process and the application of the product, because we'll be monitoring temperatures and engine speed. This test was done with the use of an oscilloscope, looking at the relationship of the air mass meter. You'll recall I mentioned the importance of the air mass meter in the calculation, the algorithms which the ECU looks at to establish the condition of the DPF and fueling functionality. So the air mass meter is represented by the red image, and the blue image represents the voltage output from the differential pressure sensor. Now, let's just clarify how this voltage changes. If there is no pressure above that of atmospheric pressure, the voltage will be low. As the pressure increases, the voltage will increase proportional to the differential or total pressure in the exhaust system. Now, as you can see from this image, there is a very large change between the voltage here represents what we call plausibility. That's key on, engine off. There should be no pressure reading. So I'm not going to go into a full diagnostic training session here, but it's important that your first observation is what pressure value you get with the ignition key turned on and the engine off, and it should read 0. When you start the engine at idle, the pressure should still effectively be 0 or very, very close to it. Two very important observations. We then open the throttle fully. This is done with a static vehicle in the workshop, and we monitor the range of pressure change reported as a voltage. And you can see from this that the change is actually quite dramatic. The scaling on this image is 5 volts. The sensor operates from 0.5 to 4.5 volts, and we have at the peak almost 4 volts coming back from that sensor. So if you imagine you have 0 pressure and 1 bar atmosphere, above atmosphere, represents 4.5 volts, we've nearly 4 volts of value. That in actual pressure in the DPF is probably around 750, 800 millibars, 0.8 of an atmosphere. That is badly blocked. We're aiming for a functional system of around 150, maybe 200 millibars total pressure when delivered on the road. So it's very, very important that that pressure is at a minimal value. This is not. You'll notice that the relationship between the air mass meter and the pressure sensor is very close. It shouldn't be. The pressure should be low, the air mass meter should be high. Clearly, this is a very badly blocked system. That said, let's introduce the actual process now. David, my son, is going to assist operating the throttle because we're going to change the engine speed. If you recall, we're going to start by loading the DPF at 1500 RPM, matching engine speed and manifold vacuum, because we've now created a vacuum because of the Venturi we've introduced into the air intake system. So a little short break while we set this up, run the engine, and then we'll come back and talk through the actual introduction of the product into the vehicle. Welcome back to the all-important part of this presentation, which is the introduction of the process of converting carbon or soot into CO2. Let me begin by saying that we're very proud and very pleased to be working with our friends from Kansas in developing this process, and David the Son's been working very closely with the technicians from BG yesterday and the day before. So we say, very, very pleased to have this association. I'm very honoured to be offered the opportunity. On with the process. What we're doing at the moment is, whilst off camera, we've been building up the temperature of the DPF, the internal temperature, without any product going through the engine system. We need to get it hot. We need to establish the correct vacuum in the manifold by adjusting and selecting the right vortex generator and setting the engine speed. The engine speed at the moment is around 1500 RPM. The temperature now is just under 200 degrees. It has peaked at around 255, 260. It's important you get the temperature as high as is possible at this phase before introducing the product. This stage of the process is to deliver the product and saturate the DPF. This is done with the highest possible temperature at the lowest possible engine speed. All I need to do now, turn the control valve on. The product should now be being delivered into the engine intake system. On the delivery hose, there is a sight glass to show flow. So you may want just to have a look at that and ensure that you have flow taking place. The moment the engine's running at 1500, it may take 15, 20, 30 minutes to reach a point where there is enough saturation in the DPF so that the second phase of this process, which is to turn off the product and increase the engine speed, therefore driving the temperatures in the DPF much higher. What we're achieving here is a regeneration process with no intervention from the engine management system. So we don't need a scan tool, we don't need any other means of driving this temperature up, only by using the delivery mechanism, the choice of Venturi and engine speed. So at the moment we're just waiting for this temperature increase. Welcome back to this very crucial part of the process. We're at the end of the loading process. The car now has been running for about half an hour with product being delivered into the engine system. Bear in mind that the control of that is engine speed, the size of the orifice in the vortex generator and the jet size. And we've achieved a temperature now of just under 500 degrees. And it's important that you see this before we move on to the next stage, which is to turn the product off and then increase engine speed, having loaded the DPF with product. That will raise the temperature even more, and that's where the conversion, the recovery part of the process is stage 2, to convert that soot into CO2 and remove the excess pressure by converting the soot, the blockage. The pressure then will reduce in the DPF and the system then will have received a full service. Welcome back. Having achieved and completed the loading stage of the DPF, we're now at the beginning of the recovery phase, stage 2. At this point, having achieved around 500 degrees, I'm going to turn the product off. I'm going to ask David to increase the engine speed to about 3000 RPM and then carefully monitor the increase in temperature. We're hoping to drive this to maybe 500, 600, 700 degrees. This may take some time, so what we'll do is a short cut while this process is being achieved, and then we'll come back and review the results of that recovery process. Welcome back once again. Now, you appreciate off camera, we've run this engine to achieve a temperature in the recovery process of 724 degrees. So in effect, we are mimicking active regeneration with no intervention from the ECU or a scan tool. The point of this, as I keep saying, is to convert soot into carbon dioxide. So the time that this takes may vary from one engine application to another. The important thing is to achieve the temperature with increased engine speed, correct selection of air metering, the correct amount of product and jet size. So all these are variables to achieve in stage 1 saturation and stage 2 an increase in temperature. And we are now at that point. This process will then continue until the pressure, the blockage, has been reduced and eliminated. And we're at that phase now. We've now arrived at the definitive point in the service that we've applied to this vehicle. I'm very, very encouraged with the results. I'd like to share those results with you and just do a little review of what we've done, what we've achieved, and what the final process is in the complete service. First of all, let's have a look at the results pre-service. You recall that I explained that the relationship of pressure in the blue image closely matched the air mass meter, and that proves that with an increase in volume, engine speed, that the pressure build-up was excessive. That's the wrong characteristics. We have a block DPF. Having gone through the loading stage, you recall that we ran the engine at low speed with product going into the vehicle, the engine system, to saturate the DPF. We then turned the product off, increased the engine speed, and then drove the temperature up to around 700 degrees. Now, at that sort of temperature, the conversion of soot into CO2 becomes very, very effective. The proof of that, of course, is carefully monitor EGTs and carefully monitor a reduction in pressure. So whilst this has been going on, off camera, we have been monitoring those two values very carefully. The result. Now, if you look at the relationship of these two images, you can see that the profile of the air mass meter has actually improved. In other words, the shape has become more aggressive. The air mass meter was somewhat subdued because obviously if there's a pressure blockage within the exhaust stream, you're not going to draw air in on the intake stream. So the signal's depressed. Having reduced the pressure, the profile's increased. And look at your pressure. The pressure now has diminished. And you can see that the differential between pressure at idle and the increase in throttle is now minimal. We've now achieved a voltage of around, I think it's about 1.2 volts. No, it's actually lower. It's below 1 volt. So we've reduced that pressure reading from around 4 volts, 3.9, to below 1 volt. So you're looking around 100 millibar of pressure. So we've gone from 800, 0.7, 0.8 in atmosphere, down to 0.1. 150 is an excellent result. Below that is an incredible result. So very, very encouraged. So how do we complete the service? Bear in mind that this service has been a total process. Bringing this product into the engine intake system cleans the entire system, manifolds, swirl flaps, EGR valves, variable vane turbo, functionality, right through into the DPF. It cleans all of those components very effectively. The final stage in the service is, of course, to drain the oil, having applied a 109 treatment. This is engine performance restoration product. It improves combustion. It cleans the deposits from within the engine system, the valves, the tappets, piston rings, etc., so that when we drain the oil, all of those deposits are removed from the engine before we apply the correct low ash C3 oil and the change of oil filter, of course. therefore completely restoring and maintaining the mechanical efficiency of that engine for an extended period. And that's the extension of that period that's quite an important point. We don't want this vehicle back with the same problem after a short journey interval. The whole method we've used is very effective at maintaining good results in performance, fuel economy, and a much improved drivability experience from the vehicle owner. So it's important we do a 109. I would suggest we don't use the 109 whilst the service is being achieved, because we don't want any crankcase emissions to affect the stoichiometric fuel ratio during the service. So this is done after the intake system service, not during the same period. I'd like to conclude this presentation by thanking our friends and colleagues at BG over in Wichita in Kansas. We've enjoyed working with them over the last 2 or 3 days. David particularly has, I think, created quite a friendship with some of the technicians during the process that we've helped develop. I've enjoyed making this presentation. I've learned an awful lot. I hope you've equally have learned as much as we have during this presentation. I hope that you will visit us again soon. Log on to autoinform.co.uk, and I look forward to presenting something new in the future.